Welcome. This question says a coil of wire consists of 10 turns. The strength of the magnetic field that passes through the coil is 12 Tesla. The magnetic field is perpendicular to the plane of the coil. The coil has an area that changes from 3 square meters to 7 square meters in 5 seconds. Everything else stays the same. So the magnetic field stays the same, the number of turns stays the same. What is the magnitude of the EMF induced in the coil? So if I imagine drawing the coil, so here's my coil, and I know the number of turns N. Number of turns, number of loops, number of windings, all the same thing, is 10 turns. You know, it's wrapped around 10 times. And what I have is a magnetic field, so let's draw that magnetic field. The magnetic field is perpendicular to the plane of the coil, so it's going to be perpendicular to that, that's my B. And so my B is equal to 12 Tesla. And then I have an area, and somehow I have a mechanism by which I can make this area get bigger or smaller. And in the book it talks about basically having a slidable rod, so this rod can move backwards and forwards, and so the area inside can change larger or smaller. You know, I've drawn it as a coil, but you know, we can imagine. So the initial area A initial is equal to 3 square meters, and the A final is equal to 7 square meters, and the time that takes is 5 seconds. So we need a principle, and the principle is Faraday's law. E is equal to minus n d phi b by dt. And let's remind ourselves, phi is the flux, it's the number of magnetic field lines I can imagine going through that thing. And my phi b is equal to, well, it's going to be the magnetic field strength dotted with the area vector. And the area vector is a vector which has a magnitude equal to the cross-sectional area of the coil and a direction which is perpendicular. So if that's my setup, there's my area vector. I can expand this, of course, and this would be the magnitude of B times the magnitude of A times the cosine of the angle between these two vectors. And if I look down here, then my B vector in this example is parallel to my A vector because it says the magnetic field is perpendicular to the plane of the coil. The magnetic field is perpendicular to the plane of the coil, and the area vector is by definition perpendicular to the plane of the coil. So these two guys are parallel to each other. Okay, so now we can manipulate and do all that kind of stuff. So let's have a look at this. So my E is equal to minus n d by dt of BA cosine that angle. So this equals minus n, and that B is going to be constant, so let's bring that out. That cosine theta is going to be constant, so let's bring that out. So we end up with dA by dt. So my EMF is equal to minus n B cosine theta, and that's going to be times delta A by delta t, which equals minus n B cosine theta A final minus A initial over the amount of time taken. So let's put some numbers in. So my EMF is equal to minus, well, my N was 10. And my B, my magnetic field strength, is a constant 12. And my cosine theta is going to be cosine, and we said that theta, the angle between these two guys, was 0 degrees, times my final area is 7 square meters and my initial area is 3 square meters over the time taken is 5 seconds. So that's going to be minus 10 times 12. Cosine of 0 is 1 times 4 over 5. So my EMF is equal to minus, let's have a look, 10 times 12 is 120, 5s into 120 is 24. 4 24s is 80 plus 16, 96. That's going to be minus 96 volts. And it actually asks for the magnitude, so E mag is equal to just the numerical value, 96 volts. And that negative sign is there so that I know this changing area within a magnetic field induces a current flow around this loop. And we can picture the current flow, the induced current flow, has been caused by an induced EMF. And so I need to know which direction to put that induced EMF. Do I get a clockwise current flow or a counterclockwise current flow? And that sign convention takes care of that. So, there I have it.